So next I am going to discuss one problem in elastic one-dimensional collisions based on the second special case which I have discussed in the previous class. Look at the problem on the screen. I am going to read out the problem. Body of mass m1 moving along a smooth horizontal surface makes a head-on elastic collision with a stationary body of mass m2. Find the ratio m1 by m2 if after the collision. First part of the question, the two bodies move in opposite directions with equal speeds. Second part of the question, the two bodies move in the same direction with linear speeds in the ratio 1:5. The mass m1, third part of the question, the mass m1 rebounds with 1/3 of its initial speed. So now first I am going to solve the first part of the question here. So here the second body is initially at rest. You can solve the problem by two methods. So one method is using the direct expression for V1 and V2 in terms of the masses m1 and m2 and initial speed u1 of the first body before collision. So if the initial or second body before collision is 0, in the special case 2 which I discussed earlier, you can write v1 equal to m1 minus m2 by m1 plus m2 into u1, and v2 can be written as 2m1 by m1 plus m2 into u1. So you are asked to find the ratio m1 by m2 if the two bodies move in opposite direction with equal speeds. That means v1 and v2 are equal in magnitude but oppositely directed. That means you have to find the ratio m1 by m2 if v1 equal to minus v2 mathematically. So that is m1 minus m2 into u1 by m1 plus m2 is a negative of 2m1 by u1 by m1 plus m2. So u1 by m1 plus m2 is a common factor on the two sides of the equation. So m1 minus m2 equal to minus 2m1. So you can carry the terms containing m1 to the left hand side and terms containing m2 to the right hand side. So you get 3m1 equal to m2, or m1 by m2 is 1 by 3. That's the answer for the first part of the question. This first part of the problem was also given in the MSET earlier, I think in 2000 or 2001 MSET in the medical entrance. It was given. You can also solve this problem by an alternate method, because some of the students may not be able to exactly remember the expressions, direct expressions for V1 and V2. So we can also solve this by another method, which I would like to discuss now. In case you want to copy the solution of the problem, you can take a pause and copy the solution of the problem. So I am discussing the alternate method for same problem now. In a one-dimensional collision, you can write m1 v1 plus m2 v2 equal to m1 u1 plus m2 u2. So here the two bodies move in opposite direction with equal speeds after collision, and second body is initial at rest. So u2 is 0. You can write v2 equal to minus v1. So therefore you get m1 v1 plus m2 into minus v1 equal to m1 u1. The second term on the right side becomes 0. So you get m1 minus m2 into v1 equal to m1 u1. You can call it as equation number 1. In a head-on elastic collision, that means one dimensional elastic collision, you can write v2 minus v1 equal to u1 minus u2. So in this case, v2 is same as minus v1 on the left side, as I have written here. You can write u2 is 0. So you get minus 2v1 equal to u1. So you can substitute the value of u1 from, or v1 in terms of u1 from second equation into the first equation. So m1 minus m2. So you can write v1 equal to minus u1 by 2 equal to m1 u1. So you get m1 minus m2 equal to minus 2m1. Can next collect the terms containing m1 to the left hand side and m2 to the right side. So you get 3m1 equal to m2, or m1 by m2 is 1 by 3. That's the answer. Want to copy this solution by the alternate method also? You can take a pause and copy the solution. Now look at the second question here in the problem. You have to find the ratio m1 by m2 if after the collision the two bodies move in the same direction with linear speeds in the ratio of 1:5. So that means here v1 is to v2 is 1:5, because the two bodies are moving in the same direction. Need not put any negative sign here. v2 can be taken as 5 times v1. Now we can substitute here v1 equal to, on the right hand side, m1 minus m2 by m1 plus m2 into u1. On the left hand side, v2 can be written as, if u2 is 0. As already discussed earlier, if the initial loss of second body is 0 in a one-dimensional elastic collision, then v1 equal to m1 minus m2 by m1 plus m2 into u1, and v2 equal to 2m1 by m1 plus m2 whole multiplied by u1. So you can substitute this value of v2 on the left side here. 2m1 by m1 plus m2 whole multiplied by u1. So m1 plus m2 gets cancelled. u1 can be cancelled. So you get 2m1 equal to m1 minus m2. Of course, there should be 5 here on the right side, because v2 is 5 times v1. So this here to simplify. If you want to copy the solution of the problem, you can take a pause and copy the solution of the problem. So you get m1 by m2 equal to 5 by 3. You can also solve this problem by the alternate method. So I would like to discuss the second problem by the alternate method also. So in a one-dimensional elastic collision, so V2 minus V1 equal to U1 minus U2. So in this problem, second body is initial at rest, and V1 and V2 are in the ratio 1:5, or V2 is 5 times V1. You can substitute these values in this equation. V2 equal to 5 times V1 on the left side, and U2 equal to 0. So you get 4V1 equal to U1, or V1 is U1 by 4. That is one equation. And in any one-dimensional collision, we can write M1 V1 plus M2 V2 equal to M1 U1 plus M2 U2. So here you can substitute from V1 equal to U1 by 4, V2 is 5 times V1. 5 times V1 is 5 U1 by 4. If you substitute V1 equal to U1 by 4 in this equation, substitute these values here. So V1 equal to U1 by 4, and V2 equal to 5U1 by 4 on the left side. On the right side here, you can substitute U2 equal to 0. So you get U1 by 4 equal to M1 plus 5M2 equal to M1 U1. So U1 is a common factor, can be cancelled. So now you can cross multiply and simplify this. So even if you want to copy the solution by the alternate method also, you can copy the solution. If you need more time to copy the solution, you can take a pause and copy the solution. So you get the same answer, M1 by M2 equal to 5 by 3. Now look at the third part of the problem here. The third problem, you are asked to find the ratio M1 by M2 if after the collision the mass M1 rebounds with 1/3 of its initial speed. So here also you can solve the problem by any one of the two methods. The initial or second body is 0. In a one-dimensional elastic collision, V1 equal to M1 minus M2 by M1 plus M2 into U1. Given that the first mass M1 rebounds with 1/3 of its initial speed. That means after the collision, the first mass moves opposite to the original direction of the motion with 1/3 of its original speed. So if U1 is the speed of M1 before collision, or velocity of m1 before collision. Second mass m2 is initial at rest, and after collision the first mass m1 rebounds back. That means moves opposite to original direction. It's 1/3 of initial speed. Therefore, you can write here v1 equal to 1/3 of minus u1. You can substitute here v1 equal to 1/3 of minus u1 on the left side. So u1 gets cancelled. So you get m1 plus m2 equal to minus 3 times m1 minus m2, or m1 plus m2 can find the ratio m1 by m2 will get 1/2. Just like the previous two problems, here also you can solve the problem by the alternate method also, which you can try to do it yourself. The alternate method should be preferred in board examination in case you are given a similar problem in intermediate board examination. If you want to copy the solution, you can take a pause and copy the solution. Now you can, after completing the problem, you can stop writing, just again concentrate only to listen. Next I am going to discuss about one-dimensional inelastic collisions. As I discussed earlier, in a perfect elastic collision, the total kinetic energy of the two colliding bodies just after the collision, same as the total kinetic energy of the two colliding bodies just before the collision. If the collision is not elastic, or we can say the collision is said to be inelastic, if the total kinetic energy of the colliding bodies undergoes a change after collision, I mean if the total kinetic energy of the two colliding bodies just after collision is not same as the total kinetic energy of the two colliding bodies just before collision, then it is said to be inelastic collision, or some of the books they write it as semi-elastic, but inelastic collision will be the more appropriate word. But this, the formula for the equation which we can commonly use for all one-dimensional collisions is m1 v1 plus m2 v2 equal to m1 u1 plus m2 u2. All of you just concentrate only to listen. Don't write the running notes when I am discussing, because you will be shown the notes later. You will be shown the PowerPoint presentation of the notes. So this equation which I have written on the screen, m1 v1 plus m2 v2 equal m1 u1 plus m2 u2, holds good for all one-dimensional collisions, irrespective of whether it is elastic one-dimensional collision or inelastic one-dimensional collision. As I discussed in the previous class, I have discussed in the previous classes that in the case of one-dimensional elastic collision, the magnitude of the relative velocity between the two colliding bodies just after collision, same as the magnitude of the relative velocity just before the collision. So in a one-dimensional elastic collision, as I discussed the theory of elastic one-dimensional collisions in the earlier classes, we write V2 minus V1 is equal to U1 minus U2. The relative velocity between the two colliding masses just after collision we call relative velocity of separation. The relative velocity between the two colliding bodies just before collision we call relative velocity of approach. So in a one-dimensional elastic collision, the magnitude of the relative velocity of separation between the two colliding bodies just after collision, same as the magnitude of the relative velocity of approach between the two colliding bodies just before collision. So Newton conducted a number of experiments on one-dimensional collisions. So Newton has selected solid spheres to study the one-dimensional collisions. He made the two spheres to move along the same line before and after the collision. The Newton allowed to collide the same two spheres with different initial speeds moving along same line, along a groove. And in each case, we compared the relative velocity of separation between the two colliding bodies with relative velocity of approach. So Newton conducted a number of experiments on one-dimensional collisions. Newton selected solid spheres and he made them to collide with different initial speeds along same line. And in each case, he compared the relative velocity of separation after collision with the relative velocity of approach before collision. So Newton, based on the experimental observations, he concluded that so for a given pair of solid spheres or colliding bodies, the ratio of the magnitude of the relative velocity of separation after collision and magnitude of the relative velocity of approach before collision is found to be a constant for a given pair of colliding bodies. So Newton's experimental formula or Newton's experimental result for one-dimensional collisions Newton's experimental formula or experimental result for one-dimensional collisions is V2 minus V1 equal to E into U1 minus U2, where E is a constant for a given pair of colliding bodies. This E is called as coefficient of restitution. E is called as the coefficient of restitution between the two colliding bodies, which you can write it as V2 minus V1 divided by U1 minus U2. Our coefficient of restitution between the two colliding bodies is equal to ratio of the magnitude of relative velocity of second body with respect to the first body after collision, and magnitude of the relative velocity of second body with respect to the first body just before collision. So E is a constant for a given pair of colliding bodies. So if you compare this equation with this equation, you can observe that in the case of one-dimensional elastic collision, the coefficient of restitution becomes 1. So in the case of one-dimensional elastic collision, E can be taken as equal to 1. Now, mathematically, it can be shown that for given masses m1, m2 of the two colliding bodies, and for given initial velocities u1 and u2 along same straight line, maximum possible loss of kinetic energy takes place when the two colliding bodies stick together or move together after the collision. So in the case of one-dimensional collision, it is observed that for given values of m1, m2, u1, u2 between two colliding bodies, greatest possible loss of kinetic energy takes place, or maximum possible loss of kinetic energy takes place. The two colliding bodies stick together or move together after collision with a common velocity. So such a collision where the two colliding bodies stick together or move together after the collision is said to be a completely inelastic collision. So in the case of a completely inelastic collision, you just concentrate only to listen. Don't write running notes. I will show you the notes later. You can write V2 equal to V1 and E equal to 0. So I would like to calculate the kinetic energy lost in the case of completely inelastic one-dimensional collision. So in the case of completely elastic collision, E is 1. For completely inelastic collision, E is 0. So in general, for one-dimensional collision between two spheres or between two colliding bodies, E lies between 0 and 1. So in the case of completely inelastic, one-dimensional or head-on collision, V2 equal to V1. Let V denote the common velocity. For any one-dimensional collision, you can write m1 v1 plus m2 v2 equal to m1 u1 plus m2 u2. So substituting here v2 equal to v1, v2 equal to v and v1 equal to v here. And you can write m1v plus m2v equal to m1 u1 plus m2 u2, or m1 plus m2 into v equal to m1 u1 plus m2 u2. So common velocity v of the two colliding bodies after the collision given by m1 u1 plus m2 u2 by m1 plus m2. So initial kinetic energy of the two colliding bodies before collision, I do not mark K, I suppose. That case equal to half m1 u1 square plus half m2 u2 square. The final kinetic energy of the two colliding bodies after collision, I do not mark K subscript F. That is equal to half m1 v square plus half m2 v square, or half m1 plus m2 into v square. Can write v equal to m1 u1 plus m2 u2 by m1 plus m2. So the final kinetic energy just of the two colliding bodies just after collision can be as half of m1 u1 plus m2 u2 by whole square by m1 plus m2. So kinetic energy lost in the case of completely inelastic one-dimensional collision or head-on collision is equal to Ki minus kf. So here ki equal to half m1 u1 square plus half m2 u2 square. Kf equal to half of m1 u1 plus m2 u2 whole square by m1 plus m2. So this you can try to simplify it. If you are interested to do the calculation yourself, you can do it on rough papers. So of course, I will show you the note systematically later. You can simplify it further and complete the calculation yourself in case you are interested to do the mathematical calculation completely. You have to simplify this whole thing. You can do the simplification on rough paper separately. You get m1 m2 by m1 plus m2 into u1 minus u2 whole square. So in any one-dimensional collision, any problem in one-dimensional collision can be solved basically by using these two equations. m1 v1 plus m2 v2 equal to m1 u1 plus m2 u2 and v2 minus v1 equal to e times u1 minus u2. That means any problem in one-dimensional collisions can be solved by using these two equations. If the collision is perfectly elastic, you can take E as 1. The collision is completely inelastic, then you can take E as 0. For other inelastic collisions, E lies between 0 and 1. So if you can solve these two equations, you can solve these two equations the same manner I have solved the same two equations with E equal to 1 in the case of one-dimensional elastic collisions. So repeating the same procedure as I discussed earlier, of course, we don't have the derivation for expressions of V1 and V2 for one-dimensional inelastic collisions in board exams, but still I would like to just discuss it. So you can solve, of course, you need not try to remember the expression for V1 and V2, which I am going to write now, but I would like just write in the results which you get in case you solve these two equations in letter notation. So any problem in one-dimensional collisions can be solved by using these two equations. If you solve these two equations for V1 and V2, you get V1 equal to m1 minus em2 into u1 by m1 plus m2 1 plus e into m2 u2 by m1 plus m2, and you get v2 equal to 1 plus e into m1 u1 by m1 plus m2 plus m2 minus em1 into u2 by m1 plus m2. In the case of elastic one-dimensional collisions, E becomes 1. If you take E equal to 1, you can arrive at the same equations which I have discussed before. So substitute E equal to 1, you will get V1 equal to m1 minus m2 by m1 plus m2 whole multiplied by u1 plus 2m2 u2 by m1 plus m2. And here also if you substitute E equal to 1, you get V2 equal to m1 u1 by m1 plus m2 plus m2 minus m1 into u2 by m1 plus m2. So you can calculate total initial kinetic energy system of the two colliding bodies before collision is given by denoted by Ki, that is equal to half m1 u1 square plus half m2 u2 square. Total final kinetic energy of the two colliding bodies just after collision is given by half m1 v1 square plus half m2 v2 square. So kinetic energy lost in the one-dimensional collisions in one-dimensional Ki minus Kf. If you substitute these values of Ki and Kf and you express V1 and V2 in terms of U1 and U2 and do the simplification is very lengthy. Only to give you the idea, I'm discussing the procedure. So, and this part of calculation is not included board examinations, but we discuss only keeping of entrance examinations. So you get half m1 m2 by m1 plus m2 into u1 minus u2 whole square into 1 minus e square. So that is the expression for kinetic energy lost in a one-dimensional inelastic collision. So for given values of m1, m2 and u1 and u2, you can observe that the kinetic energy loss will be maximum when this term 1 minus e square is maximum. So 1 minus e square is maximum when e square is minimum. So for given values of m1, m2 and u1 and u2, the kinetic energy lost in the one-dimensional collision is maximum when the value of 1 minus e square is maximum or e square is minimum. Minimum value of e square is 0. That means for given values of masses m1, m2 and initial speeds u1 and u2 before collision, initial loss u1 and before collision. So kinetic energy lost in the one-dimensional collision will be maximum when e square is minimum, when e square is 0 or e is 0. E is 0 in the case of completely inelastic collision. So the two colliding bodies stick together or move together after collision, then E will be 0 because V2 and V1 will be equal. Then greatest possible loss of kinetic energy takes place. That's why the two colliding bodies move together or stick together after collision, we call it as completely inelastic collision. So next I am going to summarize the discussion I have done for inelastic one-dimensional collision. That is, I am going to show you the notes for inelastic one-dimensional collision. So those who are writing the notes, they can get ready with your notebook and pen. Come on, look at the screen. So I am going to show you the notes for what I have discussed so far about inelastic one-dimensional collisions. So I will read out the notes now here. Those who are writing the notes, they can start writing the notes now. Newton's experimental formula for one-dimensional collisions is Newton's experimental formula for one-dimensional collisions is V2 minus V1 equal to E times U1 minus U2, or you can also write as minus E into U2 minus U1. Where E is a constant for a given pair of colliding bodies, which is called as coefficient of restitution between the two colliding bodies. So coefficient of restitution E can be written as V2 minus V1 by U1 minus U2, or E equal to modulus of V bar 2 comma 1 divided by modulus of U bar subscript 2 comma 1. V bar subscript 2 comma 1 represents relative velocity of M2 with respect to M1 just after collision. U bar subscript 2 comma 1 represents initial velocity of M2 with respect to M1 just before collision. Come on, finish copying this up to here. In case you need more time to copy the notes, you can take a pause and take your time. I am going to show you the notes continuation to this. In a perfect elastic collision, V2 minus V1 equal to U1 minus U2 and E is 1. The two colliding bodies stick together after the collision, then the collision is said to be completely inelastic. Then V2 equal to V1 and E is 0. So in general, for a one-dimensional inelastic collision, E lies between 0 and 1. So those who are writing the notes, come on, can take a pause and complete writing the notes up to here. In case you need more time to copy the notes, you can take a pause. I am going to show you the continuation for this. Kinetic energy lost in one-dimensional completely inelastic collision. That is when E is 0. Equal half m1 m2 by m1 plus m2 into u1 minus u2 whole square. Kinetic energy lost in one-dimensional collision is equal to KEI minus KEF. That you can write half m1 m2 by m1 plus m2 whole multiplied by u1 minus u2 whole square. Then which is multiplied by 1 minus e square. Come on, finish copying up to here. In case you need more time to copy this, you can take a pause and take your time. So if you solve the equations for V1 and V2, I told you that you get expression for V1 and V2 in this way for one-dimensional elastic collision, but it's not compulsory that you should copy these results. It is difficult for you probably to remember these results, and it may not be not necessary to solve any particular problem. But of course, you may be able to solve more faster some questions by remembering this, but it may be difficult for most of us to remember this. You need not try to remember. As I discussed, any problem one-dimensional collisions can be solved by using the two equations m1 v1 plus m1 2 v2 equal to m1 u1 plus m2 u2 and v2 minus v1 equal to e times u1 minus u2. So in my next class, I will be discussing one special case in one-dimensional inelastic collision where a rubber ball is dropped from certain height onto a horizontal floor and allowed to collide repeatedly.